Hello everyone, in this video we're going to be talking about E2 mechanism, and in a separate session I'll talk about an E1 mechanism. So let's talk about a general reaction of an E2 mechanism. So as the name specifies, we're going to have an elimination reactions as the part of E here. And in a typical elimination reaction, suppose I got some sort of alkyl halide, and I'm just going to draw a secondary alkyl halide with a leaving group here. And suppose I got a chlorine as my halogen there, I'm going to be using a base in elimination reactions instead of a nucleophile. But then keep in mind, some bases are strong nucleophiles and also strong bases at the same time. But suppose I'm just using some sort of base here, and I'll give you an examples later on. And what it's going to do, it's going to remove a proton, and it's going to remove, and in the process, it's going to also remove the chlorine. And these are also going to be called dehydrohalogenation reactions because you're losing the proton and you're using the halogen, and in the process, you're going to making an alkene. Um, Now, which particular proton are you really going to be removing? That's the important thing. And there is a term called a beta elimination, and you want to make sure you know what your beta protons are in a particular structure. So your beta proton is going to be the protons that are going to be connected to the adjacent carbon. So in this case, I have two carbons that are going to be adjacent to the carbon that's bearing the halogen. So I got a carbon on the left side and I got a carbon on the right side. So both of those are going to be counted as your beta carbons, and those protons on those beta carbons are going to be called the beta protons. So I have, two protons right here, and obviously I got three protons right there. And I could remove any one of those, and which one it's selectively going to remove, we'll talk about those later on. But generally, what happens, the base comes in and grab one of those protons, like in this case, suppose I grab the one that's on the right side, and it's going to go, the bond between the carbon and the hydrogen is going to break, and it's going to go in there to create the double bond there, and at the same time, this chlorine is going to leave. So this reaction mechanism is kind of similar to an SN2 mechanism where everything takes place in one step, and that's exactly what's happening here. The base is grabbing the proton, and the double bond formation and the loss of leaving group, all of those things being taken place at one step. So then at the end of the day, you're going to be making this alkene here. That's going to look like this. Now, what kind of alkene you're going to be making in terms of cis trans or Hoffman or Zaitsev product, we talk about that later, but this is just a generic reaction of an elimination where you have to have a strong base and you have to have a leaving group, obviously, in the alkyl halide for this process to take place. So the take-home message for right now is be able to identify your beta protons and be able to identify which protons could be removed, and you have a possibilities of making multiple products. And later on, we'll learn which particular product is going to predominate based on the nature of the base and based on the stereochemistry of the given alkyl halide. Okay, so let's move on why this thing is going to be called an E2 mechanism. And obviously, the E is going to be coming from the word elimination, and then 2 means it's going to be a bimolecular. Just like an SN2 was bimolecular, this E2 is also going to be bimolecular. However, in case of SN2, if you recall, we depended on the alkyl halide and we depended on the nucleophile for the rate determining step. But in this case, we're going to have your kinetics going to be looking like we got rate constant K. We're still going to have some sort of substrate or the alkyl halide, but then instead of having an nucleophile, we're going to have the base here. So a strong base is needed whenever you're trying to do your E2 eliminations, and that's going to be not true for the E1 mechanism. You can do an E1 and a weaker base. For E2, you have to have a strong base in place. So this is going to be your rate law expression for E2, kind of similar to the SN2, except you have the base instead of your nucleophile. The problem arises, when do you know you're going to have an E2 or SN2? They are E2 and SN2. They always kind of compete with one another. And the question is, okay, when are you going to have an E2 and when are you going to have an SN2? Because it's also true there are some strong bases, and those strong bases are also strong nucleophiles, and I'll talk about those in a minute. Um, but the very first thing you look for is like the type of alkyl halide. And in types of alkyl halide, we know we don't really do any SN2 with the tertiary alkyl halides because of the hindrance. So suppose I have, this alkyl halide here. No, not Cl there, just in a methyl. And I'm adding an NaOH onto it. And I know the OH minus, we have learned it's a strong nucleophile, but then remember it's also a strong base. Now this really cannot do SN2 reaction because for this kind of going in there and grabbing or attacking right there is almost going to be impossible because too sterically hindered. So it's too hindered for SN2 to take place. So you can't have an SN2 there. But then instead, what happens, you can have an SE2 mechanism where if I just take the same stuff here, I'm just gonna, maybe you can just move this to the left side or to the right side here. Have a little bit of space. And then let me just copy that down here. So since it was too hindered, what it's instead going to do, it's going to look at your beta protons. So you have multiple beta protons there, but I'm going to be focusing on only one of those because they are all identical. You have methyl groups all over the places like this, and these. These are all your beta carbons, and the protons are on them are going to be equivalent. So you got one of these protons here. So instead of doing an SN2 there, because it's not possible, it's going to be going in there to grab that proton, and then that bond is going to go in there to make a double bond between the two carbons there, and your leaving group is going to leave, and all those things are being taken place in one step. So it's like SN2, it's a concerted mechanism. So now you're going to have an E2. So you're going to have an alkene made at the end of the day along with water, and you're going to have obviously like a NaCl or Cl minus. And obviously you're going to be focusing on your organic product, and you can write your inorganic products, but your organic products is going to be the major thing. So what we just learned here that, okay, we know these tertiary alkyl halides is too hindered for the SN2 to take place, but if you have a strong base there and strong nucleophile, you can easily run a you can easily run an E2 mechanism in there because it can easily go in there to grab that proton. So when we're looking at the order of E2 and SN2 with respect to the alkyl halides, we know, if you recall real quick, the SN2, they're likely to go with methyl halides and then followed by your primary, and then you can also have your SN2 with the secondary alkyl halides. But your SN2 cannot take place with the tertiary alkyl halides. But when we're looking at the order of your E2 order is actually reversed because you're going to have tertiary alkyl halides being the most sufficient in doing the E2, followed by your secondary. And you can also have a primary doing the E2 mechanism as long as you have a non-nucleophilic strong base, and we'll talk about that in a minute. And obviously, our methyl halide is not going to do an E2 because methyl halide does not have any beta carbons and beta protons, so that's not going to be happening in that particular case. So let's say, so now we know the order, and obviously we can clearly see that if you have a tertiary alkyl halide and a strong base, you can have an E2, and then we'll do a breakdown on when do you know a secondary alkyl halide can do an SN2 or an E2, and we'll do a breakdown when do a primary alkyl halide will do an SN2 versus E2. So let's talk about the next um, factor that's going to be the determining in that case, and that's going to be your nature of your bases and nucleophiles. So it's important to understand your strong bases, strong nucleophiles, or I can talk about, strong nucleophiles, weak bases, and vice versa. So let's talk about a list of where you have a strong base and a strong nucleophile. And your strong bases, strong nucleophiles are going to be something like OH minus, OCH3 minus, OCH2, CH3 minus, and those are the most common strong bases you're going to be seeing. And I would probably go ahead and write down this as well. Acetylide is another common one that you're going to be seeing in there. So these can act as your strong bases and strong nucleophiles. So let's talk about if I'm giving one of those bases, which is also a strong nucleophile, and if I'm giving a tertiary alkyl halide, then I'm going to be doing only an E2 mechanism. Okay, and then if I'm given a primary alkyl halide, then I'm only going to be doing an SN2 mechanism in that particular case. But then what about the secondary alkyl halide? Your secondary alkyl halides in those particular cases is going to be doing both the E2 and SN2, but your E2 is going to dominate there. It's going to be the major product still in that particular case. So make sure you know the criteria of, okay, when you can have an E2, when you can have an SN2 based on your alkyl halide, and then in addition to that, you're also looking at the type of bases and strong nucleophiles in this particular case. Let's talk about a set of small strong bases and weak nucleophiles. Um, Now, you maybe seen something like NH2 minus. This NH2 minus is actually can also act as a nucleophile, but it likes to act as a base more than acting as a nucleophile. It's a bad choice to do a substitution reaction with something like NH2. So when we say NH2, what does that really mean? We're gonna have something like KNH2 or NaNH2 or LiNH2. So you have to have some sort of spectator ion, so that always keep that in mind. In addition to that, the other strong small base that's going to be acting as a weak nucleophile would be the H minus. So this H minus is going to be coming from like NaH, KH. So those are strong bases in that particular case, and I can go ahead and write down NaNH2 or KNH2 or LiNH2. So any of those would be fine. So if you have these small strong bases and these going to be acting as a weak nucleophile. So obviously if you have a tertiary alkyl halide, it's still going to be doing an E2. And if you have a primary alkyl halide, your E2 is going to be the major in that case. You may see a little bit of SN2 in that case, but your E2 is still going to be the dominating in there. It's going to be a bad choice if you're trying to make a amine from an alkyl halide. It's going to be a bad choice to run an SN2 mechanism with using NaNH2, because you're always going to have a fear of running those in elimination reaction. So if you want to make an amine from a primary alkyl halide, the better way to do it is use ammonia. All right, and obviously ammonia also has some limitations in there. And if you can't use an ammonia, then use sodium azide like N3-1 minus. That's a weak base, but it's a strong nucleophile, and then you have to reduce it afterward. So that's another way of doing it. And obviously, if you have a secondary alkyl halide, it's still going to be doing an E2 here, because they're not going to be acting as your strong nucleophiles. So I can go ahead and write down here SN2, but that's going to be very minor. So that's why whenever we have done SN1 and SN2 mechanism, we didn't really talk too much about NH2 and H minus, and especially that H minus coming from these metal hydrides. They like to act more as a base than in nucleophiles. So then let's talk about strong bulky bases, and they are going to be weak nucleophiles. So this is another important class that you want to make sure you know. So this is going to be something like tert butoxide, so OCH3, something like that. So that's a tert-butyl group, and then you got an oxygen. The other common ones are going to be LDA. You got a DBU. You have DBN is another one. So you don't really have to know how their structure is going to be looking like, but for the most part, you're going to be seeing those in the class where you have written LDA or DBN or DBU, stuff like those. So those are your strong bases, and they're weak nucleophiles. So if they are weak nucleophiles, it's unlikely they're going to be doing any SN2 types of reactions, because they don't really like to act as a nucleophile. There are going to be some minor conditions when they can act as nucleophiles, but for the most part, they're going to be acting as your bases. So if you have a tertiary alkyl halide, it's still going to be doing an E2. If you have a secondary alkyl halide, it's going to be still doing an E2. And if you have a primary alkyl halide, it's still going to be doing an E2 completely. No SN2 in this particular case. Like when we talk about those small, strong bases, especially in case of this NH2 minus, you're always going to have a little bit of fear that it may run a little bit of SN2 there, but in case of these bulky strong bases, they're not going to be doing any SN2 mechanism in there unless you have a methyl halide. If you have a methyl halide, then you obviously don't really have any place to create a double bond in there. So make sure you know your selective categories of your bases and your nucleophiles in this for these reactions. Now, we talked about these small bases with these big bases, and they plays an important role what kind of product you really going to get at the end of the day. So let's talk about that, or another way of saying, let's talk about more on the mechanism. So suppose I get this product, this reactant here, and I'm trying to run an E2 mechanism on those, and I'm going to be picking up two types of bases. So I'll pick up a strong small base. So let's say I go ahead and pick up OH minus. So this OH minus, that's going to be a secondary alkyl halide. It's going to be doing an E2 as your major product. But let's just say I'm going to be looking at how your major products in the E2 among the E2 mechanism here are going to look like. Let's focus on how many beta protons you got. So I got a beta carbon on the right side, I got a beta carbon on the left side. So then I'm going to be looking at a proton right there, two protons right there, and I can go ahead and change the color there. And I got 3 protons on the left side. So then the question is, which one it's really going to remove? Because it has the possibility of removing both of those protons, and turns out if you're using a small base, when you use a small base, the small base has this tendency to go in the crowding places and remove a proton so that you make the most stable alkene. So since this is a small base, it's going to go in there to grab one of these protons that's going to be on the right carbon, and then this goes in there to create the double bond, and that's going to leave. And in the process, it's going to make this alkene that's going to be more substituted. Okay, it's acting up. So you're going to have a double bonded alkene here, and I'll talk about the stereochemistry in a little bit, but right now I just want to focus on the regioselectiveness of these E2 mechanisms. So it rather pick the proton from the right carbon so that it can make a more substituted alkene. So what does that really mean when we talk about more substituted alkene? Well, I clearly have on the double bonded carbons, I got 2 alkyl groups, or 2 R groups. You can say I got an R group here and I got an R group here. So this is going to be called a di-substituted alkene. This particular product is going to be called a Zaitsev product, and Zaitsev product is going to be achieved whenever you're using a small base, unless there is going to be a restriction on the proton, and I'll talk about that in a minute, because even though when you use a small base, you may not necessarily get a Zaitsev product or a more substituted alkene. Now, what does that really mean if we remove the proton from the left carbon? So let's talk about that. I'm just going to copy this down here, and I'll erase some of that. So now all of a sudden I'm going to be using a bigger base. So let's say I use LDA. So this LDA is kind of big and it can't really go in the crowding positions. So it's going to be removing the proton that's going to be the most readily available. So between those two protons on the right carbon and on the left carbon, this proton that's going to be on the left carbon is going to be more readily available than the proton on the right carbon. So as a result, it's going to be actually grabbing this particular proton and it's going to be creating a double bond. Your chlorine is going to leave. So then now you're going to be making a alkene that's going to be less substituted. What that really means, if I'm looking at how many alkyl groups you have on the double bonded carbons, I have only one now, this particular one. The other positions are going to be filled up with the hydrogen. So I got a hydrogen here, I got a hydrogen here, and I got a hydrogen here. So since I have only one R group on those double bonded carbons, this particular one is going to be mono substituted. Okay, so this particular product is going to be called a Hoffman product, and you get the Hoffman product anytime you use a bulkier base. So remember, we classified earlier the different types of bases, the small bases and bulky bases. So remember your bulky bases, I can go back and write down, this is going to be doing a Hoffman product. And when we looking at your smaller bases, those are going to be doing the Zaitsev anytime they do a E2 mechanism. And remember, the Zaitsev is not always going to be there because there are going to be some restrictions sometimes, and I'll talk about that in a minute. So this particular um, condition where you have a possibility of removing two different types of protons and making two different types of products here. Like I have the possibility of making either a Zaitsev product or a monosubstituted product, which is the Hoffman product. And that's going to be dependent on the type of base you use. So obviously, if you're using a smaller base, then this one is going to be the major. The more substituted product is going to be the major in there. And obviously, you may get a little bit of the mono-substituted, but I'm just trying the major one. And when you're using a bulkier base, this less substituted product is going to be the major, and your other product is going to be the minor. So when you have a possibility of making two different types of products, but based on the type of base you're using, you make only one of them to be the major and the other one to be the minor. That's going to be called the regioselectiveness of these reactions. So what type of constitutional isomers you're going to be getting is going to be dependent on what type of base you're going to be using in this particular case. So that's going to be your regioselectiveness of this E2 mechanism. Now let's go back to this first reaction actually. So I'm just going to go ahead and copy this down here. When we're going back and looking at this first reaction where we used a small base and we made this di-substituted alkene, which was the major product according to the Hoffman rule, I could make two different types of products. I could make this right there, and in addition to that, I could also make a cis version of it. So when you make the first one is going to be the trans alkene, and the second one is going to be the cis alkene. So another way of saying you may be able to getting like a E alkene or a Z alkene. So in this particular case, you don't really have to call those E or Z because you got the same type of alkyl groups on those double bonded carbons. So whenever you have a possibilities of making both of those products, like this trans alkene and cis alkene, but your trans is mostly going to be the major product. So this is going to be the major product, and as a result, this reaction is going to be called an stereoselective. What that really means that I have the option of making, we got the double bond there, I have the option of making two different types of diastereomers here, the cis and the trans, but I make one more over the other one. So as a result, this reaction is going to be a stereoselective. Okay, so then these E2 reactions can also be stereospecific. So that's why there's so many things going on with these E2 mechanisms. So what does that really mean? So let's look at this particular example here. And I got a small base kind of being taken during this reaction. So let's say OCH3 minus. And I can clearly see how where my halogen is. So I got the halogen right there. and where gonna be your beta protons? Well, I got one beta carbon here and the other beta carbon here. And which one would be making the more substituted product or the Zaitsev product? Um, it turns out it's going to be the left beta carbon because you got two R groups on that. You got a methyl group, uh, here, and you got a phenyl group there. But if you look at your other beta carbon, you're only going to have one R group there, so that's going to be not going to be your most substituted product. As a result, you want to remove the proton that's going to be on the left beta carbon. Okay, well, let's say we are focused now on to grab the proton that's going to be on the left beta carbon, which is obviously going to be this proton here. But then this proton right there and this bromine, they're both going back into the page. So this is going to be called a syn periplanar, and your E2 mechanism has to be something called an anti-coplanar, or the other name for that is a anti-periplanar. So E2 needs to be anti-coplanar, and the other name for that is anti-periplanar. Now, there is a small difference between those two. Anti-coplanar is when your angle between those two atoms, bromine and your hydrogen, is exactly 180. But anti-periplanar means it could be a little bit off. It could be like, 179 or 181 or something like that. But these two terms kind of used mixed up with one another. So what I want to do is, before I do anything, since they are not opposite to one another, both of those going back into the page, I want to make sure I make those opposite to one another, or I make those anti-periplanar to one another. And there are actually two ways of doing it. And I'll show you both of those ways. The first way is I'm going to be rotating this left section here. So I'm just going to draw that. I'm going to be rotating this left section there until this hydrogen comes down to this position here. So this is something going to be a little bit hard to understand, so make sure you flip the position. So when you rotate this, your hydrogen comes down here, and then everything is going to get flipping the positions basically. So hydrogen comes down here. So when your hydrogen comes down here, you're going to have your methyl now going back into the page, and then you're going to have your phenyl coming out of the page. So another way of saying, you just rotate every single thing here. And then I'm going to be doing the same thing on the other side. I will do the same thing until this bromine and this hydrogen, they are coplanar, anti-coplanar with one another. So I want to rotate this so that this bromine comes up here, and then this group kind of be coming down here, and this hydrogen is going to be coming down here. So I'll just go ahead and draw something like this. So your bromine comes up here, and then your hydrogen is going to be coming in place of the bromine, and then your ethyl group is going to be coming out of the page in that case. So now this group, this hydrogen right there, and this bromine, those are anti-coplanar with one another, or you can say they're anti-periplanar with one another because they're opposite to one another. It's easier for this base now to grab this proton, and this is going to go ahead and create the double bond, and that bromine is going to leave. So this is always going to be the case whenever you're doing these elimination reactions. Now you may wonder why in the world we didn't really worry about earlier. Like we look at these earlier cases, we have two protons. So whenever you have two protons, it doesn't really matter because you can arrange those however you want. Or another way of saying, you have multiple possibilities of getting those two protons in the anti-periplanars. The problem arises whenever you have only one proton and you have to make sure they are going to be anti-periplanar with one another. So when this happens, how your product is going to look like now. So I'm about to create a double bond here. So I'm just going to go ahead and create a double bond right there. And you can clearly see my hydrogen was going back into the page. So I'm going to make that hydrogen, it's going somewhere. It doesn't really matter going to the top or the bottom. And then your syn to that hydrogen is going to be this particular methyl group. That methyl group and that hydrogen, they're both going back into the page. So that means they're both going to be in the same direction at the end of the day. And then you can clearly see that we got this phenyl group right there, and we got this ethyl group, they are also going to be coming out of the page, which means they are going to be in the same direction as that of the double bond. So I'm going to be having a phenyl group right here, and I'm going to be having an ethyl group right here. Okay, so this is how it's going to look like at the end of the day. And what type of products that's going to be? Is that going to be a E or Z, or another way of saying cis or trans? Since you have different substituents on those double bonded carbons, you want to call it either E or Z. And when I'm looking at my groups here, um, this phenyl is going to be 1, and this methyl on the top is going to be 2, and on the other side this is going to be 1 here, and your hydrogen is going to be 2. So you have the same type of groups on the same side, so that means this is going to be the Z form of that. So even though we said, you know, you're likely to make a transform in those elimination reactions, but sometimes it's going to be restricted because you just don't have the hydrogen and your leaving group aligned at the anti-coplanar situation. So when you do make those anti-coplanar, then they may not turn out to be the trans, they may not turn out to be the E in that case. So that's one way of looking at it. And the second way of looking at it is by drawing the Newman projection. So if I want to go ahead and draw the Newman projection of this particular one, so let's say I can probably just copy this so that I don't have too many things going on here. And let me just erase a lot of this. So let's call this front carbon, and let's call this back carbon. So when I'm looking at the front carbon, I can go ahead and draw this ethyl group kind of going out of the page, and then I can draw this bromine on one side. It doesn't really matter in the beginning, but you want to make sure you draw the other ones accordingly, and this hydrogen is going to be going to the left. So that's your front carbon. Now let's draw the back carbon. So when you're drawing the back carbon, we're going to have the hydrogen on the back carbon is going to be syn to the bromine, all right? Or another way of saying they needs to be pointed in the same direction. But one of the best way to do it is by looking at what's anti to those. So if I'm looking at this phenyl group here, this phenyl group right there and this ethyl group, they're anti-coplanar, so that means you must have a phenyl group anti here. So this is where your phenyl group going to be, and then put the other groups accordingly. So your hydrogen is going to be in the same direction as that of bromine, and then your other ethyl group or other methyl group, which is going to be this right there, and this hydrogen, they are going to be syn to one another. So you have the hydrogen right there, so that means you want to put your methyl group right here. So that's how it's going to look like, and you can see I got this bromine, that's a leaving group, and I got this beta proton, that's this right there. They are in the same direction. I can't really make those make the elimination reaction until they are anti to one another. So to make those anti to one another, what would I have to do? I gotta rotate one of those carbons, either the front carbon or the back carbon. It doesn't really matter. So let's say I rotate this front carbon by 120 degrees. So this is gonna come down here, and that's gonna come up here. Okay, and that's gonna come down here. So your back carbon stays the same. So let me draw the back carbon first. This is going to be where the hydrogen is. And you can rotate the back carbon if you want. It doesn't really matter. You're going to still end up getting the same product. And now your front carbon is going to have the new location where the bromine is going to be right here. And your hydrogen is going to be going to the top here. Oh, this should have been methyl here. My bad. So hydrogen is going to be going to the top there, and then your final group there, that's going to be the ethyl, that's going to be going this way. Okay, so now they are anti to one another, and since they are anti to one another, I can go ahead and bring in my base and grab this proton here, and this bond is going to be start creating a double bond between the front and the back carbon. So I can't really show that, but it's going to be somewhere down there, and this bromine is going to leave. So what happens at the end of the day? You clearly see that this phenyl group and this ethyl group, they're on the same side. And then you can clearly see that we got this methyl group and this hydrogen on the back and the front carbon respectively, they're on the same side, and that's how exactly you want to draw those. So I will go ahead and draw the double bond between the front and the back carbon, and now I can say, okay, so let's say this is my front carbon here. The front carbon is going to have the ethyl coming downward, and then I was gonna back carbon is going to have the phenyl coming downward here, and then the back carbon also going to have your methyl going up, and your hydrogen on the front carbon is going to be going up as well. So that's the exact structure that we have gotten earlier. I just have it flipped, but it's the exact same thing that we have gotten earlier. So this is going to be the E form. So that's another way of looking at how you're going to be doing these anti-periplanar or anti-coplanar eliminations in case of E2. Now remember, this is going to be mattering only whenever you have one beta protons and they're not anti, and it's not anti to the leaving group. In that case, you got to rotate it. This is probably going to be the most difficult thing to understand in E2 eliminations, but with practice and everything, it will be easier. Let's look at this particular question here. So we have this secondary alkyl halide, and we got this NaH. We know that's going to be a strong base, doesn't really like to act as an nucleophile. It is going to be a small base. So since it's a small base, it has the potential to do a Zaitsev elimination. But let's look at your beta proton. So I got a beta proton that's going to be right here. And I got two other beta protons that are going to be right here, one coming out of the page on the left carbon and one going back into the page. Now you can clearly see that your bromine is actually coming out of the page. So to make this hydrogen anti to the bromine, it must be going back into the page. But when you look at this example, when you look at the right side, this hydrogen is actually coming out of the page. Another way of saying both this bromine and this hydrogen, they are actually sent to one another. So that means we got to make this anti before we can eliminate this. And turns out we can't really do that because of the ring. There is going to be a restriction in the rotation in the ring. We were able to do that in the previous example because it's a single bond. You can rotate it however you want until you get those anti to one another. And in this particular case, well, we're not going to be getting that particular hydrogen anti to that bromine. So as a result, we're not going to be able to make the most substituted alkene. Because if we create the double bond right here, for example, this is going to be tri-substituted alkene. But we're not going to be able to make that because, let's say, not observed, because this hydrogen is not anti to that bromine, and as a result, what happens? This is actually going to be removing the proton from the left beta carbon. So when it removes the protons from the left beta carbon, because you have an option there, I can remove this particular one here, and this can go in there, and that would come out. Now you get a product. They get a product that's going to be less substituted. It's only going to be di-substituted. But it's okay because you don't really have an option of removing the other proton that's on the right beta carbon. So in this case, this is the only product that's going to be observed, and even though it's in a Hoffman product. So remember I said earlier that these small bases mostly give you that's a product unless there isn't a restriction there, and the restriction is going to be coming from if you don't have an anti proton with respect to your halogen or with respect to your leaving group. Finally, one of the things you want to know is how to draw the free energy diagram for these E2 reactions. Remember, the E2 reactions are going to be very similar to your SN2 reaction, where you're only going to have a one energy hump there, because this actually takes place in one step. And since it takes place in one step, you're going to have one transition state. And during the transition state, you're going to have a few things going on. You're going to have a double bond formation, you're going to have the loss of leaving group, and you're going to have the base grabbing the proton at the same time being taken place. So that's one thing you want to make sure you understand. So this is a one-step mechanism. Um, that's going to be dependent on both the reactant and your base in there, or the Rx and the base, basically. All right, so this is all you really have to know about your E2 eliminations. And obviously, like I said, the most important part is be able to understand when you're going to get Zaitsev, when you're going to get Hoffman, and be able to understand that, yes, if you're getting multiple stereoisomers where you have cis and trans possibilities, you're always going to get trans unless there is going to be a restriction, something not being periplanar like we have seen in this particular example, and be able to kind of rotate the molecule until your bromine or your leaving group and your hydrogen, beta hydrogen, are anti-coplanar or anti-periplanar. And then sometimes if they're not, you're going to be removing the protons from the other beta carbon, and that's going to be not making the most substituted alkene. In that case, you may be just getting a Hoffman product even with a small base. But if you have a big base, it's always going to be Hoffman product. Okay, if you have any questions on any of those, feel free to leave any comments in the section below.